Apologies for that. Well, firstly, it's a great pleasure to participate in this celebration of the 100th birthday centenary of Boas Trachtenbrot. And my thanks to the organizers for inviting me to give a presentation. The topic I'd like to talk about, I call relating structure to power. I think this is a topic that Boas would have appreciated. I perhaps not agreed with the perspective, but would have been a good discussion. Of course, every logician may feel that they're concerned with both structure and power as different aspects that are intertwined in their work. But I have in mind something a bit more specific to do with computer science and foundations of computer science, even specifically logical foundations of computer science. What I mean by structure is particularly work around composition, which emphasizes compositionality and semantics, and addresses questions such as how we can master the complexity of computer systems and software, leading into verification and so forth. On the power side, we have the questions of expressiveness and complexity, and how can we harness the power of computation and recognize its limits. Now, the fact that we've sort of all kind of very used to, but perhaps we should be more disturbed by, is that the current state of the art, even within logic and computer science, one could say, is without too much exaggeration, that these different aspects of the subject are studied by almost disjoint communities of researchers with little in the way of common technical language or tools. And it may be advantageous to redress this and make more such connections. I think it may be even a necessary step in order to make fundamental progress in computer science. So let me make, of course, only an analogy, but with the Grothendieck program in algebraic geometry, which developed extremely abstract tools that were ultimately critical for actually very concrete results, most famously the Wiles-Taylor proof of the Fermat-Last theorem. And here is a nice quote from a famous number theorist, Barry Mazur, quoting another famous number theorist, Henrik Lenstra. 20 years ago, he was firm in his conviction that he did want to solve Diophantine equations and that he did not wish to represent functors. And now he is amused to discover himself representing functors in order to solve Diophantine equations. So maybe if we can combine the things we've learned in these different facets of the subject, we can make progress. So now let me say a little bit about Boas. He was a pioneer of our field, foundations of computer science, logic in computer science, and he was certainly a pioneer of both these aspects, and he had a very unified vision of the field. On the power side, the famous results that have already been mentioned, Trachtenbrot's theorem on satisfiability in finite structures, the Cauchy-Elgot-Trachtenbrot theorem, MSO, and the Borodin-Trachtenbrot gap theorem, as just as famous examples of his contributions on that side of things. But then particularly in the later work, he did a lot of work in semantics, in studying the foundations of concurrency, nets of processes, semantics of data flow, and later hybrid systems, continuous time systems. Actually, I met Boas when he was working in semantics of data flow. I think Alex at the time was doing his PhD with him, and they were working in this area. We had some very nice interactions, and Boas visited me in London, where I was at the time. So he certainly studied both of these aspects, but I think the situation is as I've described it. And I think it would be of interest to develop a more unified approach. So what I want to do is to briefly present a novel approach, a recently developed approach to relating categorical semantics, which could be taken to exemplify structure, with finite model theory, which exemplifies power. And as we know, Trachtenbrot's theorem, in some sense, is the founding result for finite model theory. And the work I'm describing started off with a couple of papers. The more extensive reference is the one called Relating Structure to Power, which very recently appeared in the Journal of Logic and Computation. And I have a current EPSRC project with Anuj Dawar in Cambridge, which is, so he's really on, I mean, we're sort of reaching across this divide as we start out from different places, but there's a very nice collaboration, a number of people involved in this project. And well, here they are. So what's the point of view? I mean, the idea is we have an extensional category, the mathematical objects we want to study, and for us, there will be relational structures and widely used in constraint satisfaction, databases, finite model theory, and descriptive complexity, and so forth. And then we have what we may call an extrinsic machinery, I mean, a syntactic apparatus of logical languages with various hierarchies and fragments, such as quantifier rank, number of variables, might be modal depth or whatever. And other important machinery is games, which have been used so effectively, where we have other quantities such as number of rounds, use of auxiliary resources such as number of pebbles, and so on. So all of these syntactic descriptions or game descriptions give us access to some notion of resource. And the question is, can we give a more structural and intrinsic account of resources? And I think there are many potential benefits, but I just want to give some idea of how we proceed in this way. And as a general remark, a key ingredient is going to be the assignment of a process structure, an intentional description, to an extensional object such as a function, a set, or a relational structure. And it's this process structure unfolding in space and time to which a resource parameter can be applied, which can then be transferred to the extensional object. Now, this is really a very familiar idea throughout computability and computer science. So when we assign a machine description to a recursive function or an automaton to a language, then we can assign a complexity measure to the function. You can't ask for a function in the abstract what its complexity is, but if you know it's been computed by a machine or which machines it could be computed by, then the question makes sense. And the same phenomenon actually arises in semantics. So the famous full abstraction problem for PCF is about picking out the sequential functionals, and sequentiality is really applicable to a process computing a higher order function. And the success of game semantics was exactly to reify this idea in the form of semantics, which allowed a resolution of this full abstraction problem. So in our approach, we're going to build tree-structured covers of a given purely extensional relational structure. And such a tree cover will not have the full properties of the original structure, but be a best approximation in some resource-restricted setting. And this is made precise by saying that we have an adjunction, in fact, importantly, a comonadic adjunction yielding the corresponding comonad. So we have an extensional category, which for our purposes will always just be the category of relational structures. But the objects of the category where the approximations live have an intrinsic tree structure, which can be captured axiomatically, in fact, as arboreal categories. And that it's this tree. I mean, it could be a more general structure, but trees, as we know, work very well for many purposes. So the tree encodes a process for generating parts of the relational structure. And it's this process to which resource notions can be applied. And then we can transfer these notions to the extensional category via the adjunction. Okay, so just to briefly review the setting of relational structures. So we'll deal with purely relational vocabulary. So we only have relational symbols. And then a relational structure just has a set, the carrier, the universe, and interpretations of the appropriate arity for each of the relations in the vocabulary. And a homomorphism is a function which preserves all the relations in the vocabulary. And of course, this is pervasive in model theory, computer science, databases, constraint satisfaction, finite model theory, and also in combinatorics, where the homomorphism view of graph theory in the work of Helen Nessedrill and others has become important. So our setting will be this category of relational structures and homomorphisms, and this will be our extensional category. This one category can be viewed through many different resource-sensitive lenses, and this will be one of the points that I want to carry over. So as we said, the idea is we're going to have some tree structure. So the way we think of trees is as cosets. These are just simple, these are not, I mean, these are, I guess, well, anyway, these are trees where each element, the predecessors of each element form a finite linear order, a finite chain. So that's a forest where the minimal elements are the roots of the forest, and a tree is just a forest with a least element, which is the unique root. So a forest ordered sigma structure is a relational structure, just as we were saying, which in addition has a forest order in it. And we want to relate the relational structure with this order. And the condition we'll put here, and this is what I'm giving you, is a very basic example, from, as we'll see in first order logic. And the condition that we want to put, I'll call condition E, that the elements which are adjacent in the Geifman graph of the structure, so in other words, elements that occur together in some tuple of one of the relations in the structure, must be comparable in the order, which means they lie on the same branch of the forest. So if they can be related by basic relations, they must lie on the same branch. Now, in fact, the minimum height of such a forest order is a well-known combinatorial invariant of a structure, the tree depth, introduced by Nesetril and Osuna de Mendes. And it's in fact an important combinatorial parameter, which is used in many different ways, both in combinatorics and also in finite model theory, notably by Rossmann in his celebrated homomorphism preservation theorems. Now, from our point of view, we've just described this structures where we add to the relational structures this order with some coherence between the relations of the order. So this gives us a category which morphisms are those which preserve the morphisms are those which preserve the tree structure as well as being relational homomorphisms. And in a very trivial way, there's a forgetful functor which just forgets about the order and takes us back to ordinary relational structures. And moreover, there's a very natural resource index we can apply here by simply restricting the height of the orders that we consider. So if we restrict to forest orders of height less than or equal to k, and you can start to think that squashing a structure into an order of a certain height where related things in the Geifman graph have to be on the same branch is telling us something significant about the structure of the relational structure, and that's what tree depth is about. Anyway, if we restrict to forest orders of height less than or equal to k, we get this subcategory of so we have a natural resource indexing, and we can simply forget the ordering and go back to relational structures. Now, the beautiful thing is that if you have such a functor, you can always ask, does it have an adjoint? And if it does have an adjoint, that thing is uniquely determined. There's only one thing it can be, up to isomorphism. And this functor does have a right adjoint, which then automatically gives rise to a comonad on the category of relational structures itself. So let me briefly describe what this right adjoint is. It's quite simple to describe, and then I'll tell you why it might be of interest. So given a structure, the universe, so notice the problem we're trying to solve. Given just an ordinary relational structure, we're trying to build a forest order on it in a canonical way, in a universal way, strictly speaking, a co-universal way. So what we do is, given a structure, we build a new structure whose universe consists of sequences, non-empty sequences, and in this resource restricted version, non-empty sequences of length less than or equal to k. And this is forest ordered by the prefix order. Obviously, it's just words and ordered by the prefix order. And there's a map which simply sends a sequence to its last element. It's natural in this setting to go to the last element rather than the first, because we think of As we'll see, we can relate these to games where we think of the sequence as corresponding to successively choosing elements from the universe of A. And the key question is, how do we lift the relations on A to this new structure? And so given a binary relation, for example, we lift it to this new structure by saying that two sequences are related. Firstly, if they're comparable, if they lie on the same branch of the forest. And secondly, then, if the last elements are in the underlying relation. That's the definition. Now, the claim is that this really solves our universal problem. And this is easy to see, in fact. So we have just the category of relational structures over here. So what our universal problem amounts to is, if I'm given a homomorphism here, from just forgetting the order and just thinking of this as a relational structure and mapping it to another relational structure A, then I have to lift it in a unique way to this F hat, such that this evaluation sort of shows that it agrees with the original function F. Now, since this is a forest, given any element, it has a unique sequence of predecessors, linear order of sequences, linear order of predecessors in the ordering. And of course, we can put these in a sequence ending with the element under consideration, and that's where we send an element of F2 in here. Remember, this has as a universe a set of finite sequences. And then the way we've defined the ordering ensures, given this property E that we had, that Geifman adjacent things have to be on the same branch, that this is a well-defined homomorphism, this F hat. In fact, a morphism of forest-ordered tree structure, of forest-ordered structures, and it's easily seen to be the unique one which fulfills this universal property. Even better, this adjunction is comonadic, meaning that the category of coalgebras for the comonad we get out of this adjunction is exactly this category of forest-ordered structures that we started off with, and that will be important, as we'll see in a moment. Now, you may be thinking, well, okay, I've given you this bit of abstract nonsense, why might it be interesting? Well, the first thing to say is that this is all uniquely determined just from right adjoint is determined by the forgetful functor, the comonad by the adjunction, but also because it recovers in quite a striking way a very large and central part of first order logic. It gives us back the Ehrenfeuer-Fréissé game. It gives us back the quantifier rank index fragments of first order logic. And it gives us back the equivalences on structures induced firstly by the full fragment, indexed by quantifier rank. Secondly, the existential positive part of the fragment. And thirdly, the extension of the fragment with counting quantifiers, which is an important extension in finite model theory. Plus, we recover the important combinatorial parameter of tree depth that we've already mentioned via the coalgebras of the comonad. And moreover, this is a pattern. What we've shown here in this example is a pattern, is a template, and the same template can be used to give similar analyses of a wealth of other logical and combinatorial notions. And in fact, this general pattern has been axiomatized in a paper on arboreal categories with Luca Reggio, which appeared in this year's ICAL. Okay, so let's say a bit more about how we get all this structure out from the construction we just described. So the idea is that an element of this universe represents a play over the structure A of length less than or equal to K. And the morphism from this EK of A, this comonad, essentially think of it just as this construction with sequences and so forth. It represents a duplicator strategy for the existential Ehrenfeuer-Fréissé game with K rounds between A and B. It's existential because it's sort of going in one direction only. Spoiler always has to move in A, and duplicator always has to move in B. And the idea is that we're responding to these sequences really as it were, we're responding to the last element of the sequence, the last move in the play. And what the function gives us back is duplicator's response to the ith move by spoiler. And the winning condition for duplicator in this game, recall, is that after K rounds, the induced relation is a partial homomorphism from A to B. So our first sort of piece of evidence that we're capturing things here is that there's an equivalence between having a homomorphism from this comonad on A to B and duplicator having a winning strategy for the existential game with K rounds, Error-Free game played from A to B. And then also, of course, with the fact that every existential positive sentence with quantifier rank less than or equal to K, which is satisfied by A, is also satisfied by B. So we captured these important notions. Now, this is you might think that this is as good as it gets because we have morphisms and they're not symmetric. So how do we capture back and forth equivalence? And hence the whole logic rather than just the existential positive part. And the key idea is to work over in this arboreal category, the category with the extra tree structure or forest structure, where we have enough process structure to have notions of game and bisimulation meaningful. And the key notions that we need are paths, which are those special cases, in other words, the branches, the linear orders. So paths are branches through a forest, and if a whole structure is a linear order, then we call it a path. And then path embeddings, which are forest morphisms with paths as domains, which are also embeddings as maps of relational structures. These are path embeddings are important in letting us capture the full force of partial isomorphisms and similar notions. Now, this is all special cases of notions which can be axiomatized in the arboreal category setting in great generality. And we don't need very much in the way of general assumptions to make all of these things work. We need a nice factorization system and a few co-products. Okay, so we say that a morphism is a pathwise embedding if under composition it takes paths to paths, path embeddings to path embeddings, I should say. This is, so it's locally a path embedding. If you like, it's going to be locally a partial isomorphism. So this is going to be one part of how we define the full back and forth equivalence. The other part exploits the notion of open map used by a well-known work by Joel, Nielsen, and Winskell to give us a general notion of bisimulation. And again, this can be defined in great generality. It actually originates with Joel's work on open maps in toposes. So we say that the map is open if it satisfies the following path lifting property. I have path embeddings into X and into Y, and P is extended by, the path P is extended by Q, that's what this being an embedding means. Then there's this lift like this. So it's saying if I'm sort of matching things up with F up to P, then if I now do something in Y, I get, this is the sort of back condition in a back and forth condition, then I have this lifting which makes everything commute and which will itself be an embedding then. So this is really axiomatizing in a good way the back condition. So this is what it means for a morphism to be open. And now we can say that a bisimulation between objects is a span of open pathwise embeddings. And we say that if such a thing exists, X and Y are bisimilar. And this, firstly, we have a result that tells us this exactly hits the nail on the head for this particular example. It says that if the two things are bisimilar, well, that we can characterize exactly being equivalent or duplicator having a winning strategy in the K-round Error-Free game between A and B, if the images of A and B in the arboreal category are bisimilar in the sense that we've just described. So what we're doing is to use this resource category to study logical properties of objects of the extensional category. We study A and B in a category with enough process structure and with a resource structure, and so we can make these kind of statements. We can actually equate bisimilarity in games even at the abstract axiomatic level, as explained in the arboreal category paper. And then to see about these equivalences, we have the usual quantifier rank fragment, the existential positive part, where we only have the existential quantifier, conjunction and disjunction. And we have the extension of the quantifier rank fragment with counting quantifiers, which are important in finite model theory and its applications. And we can define 3 resource indexed equivalences on structures of the extensional category in terms of, again, what's happening in the resource category. So we have bisimilarity of their images in the resource category. We have isomorphism in the resource category, and we have just having homomorphisms in both directions. And the result is that the logical equivalences, if 2 structures satisfy exactly the same formulas of the corresponding logic fragment, are characterized by these structural equivalences defined purely from the data coming out of these resource indexed adjunctions. And furthermore, we can use the coalgebras, which is another thing which kind of follows automatically from what we've from having an adjunction and then a comonad, to study the combinatorial parameter of tree depth. So we should only expect a coalgebra structure to exist when, in some sense, the k-local information on A is sufficient to determine the structure on A. Otherwise, how would we even get such a homomorphism here? So we can ask a new kind of question, which is sort of very natural from a combinatorial point of view, but not so familiar from a category theoretic point of view. Given a structure, we can ask what is the least value of k such that a coalgebra at resource index k exists on this structure for our given comonad. Here we're studying this EK, the Ehrenfeucht-Issei comonad. And we call this quantity the coalgebra number of A. And what we get is that this Ehrenfeucht-Issei comonad, but the point is the question is completely general. But what we have in our particular example is that for this Ehrenfeucht-Issei comonad, the coalgebra number of A corresponds precisely to the tree depth of A. So this is, and this follows, in fact, from the comonadicity of the adjunction. So let me just very briefly sort of sketch one other example, namely that of Pebble Games, which is similar but also subtly different to Ehrenfeucht-Issei games. So we have the resource now is a fixed set of pebbles. Spoiler moves by placing one from this fixed set of, so it's the number of pebbles which is the resource rather than the length of the play. We could say memory in some sense rather than time. Spoiler moves by placing one from a fixed set of pebbles on an element of one structure, and duplicator responds by placing their matching pebble on an element of the other structure. And duplicator wins if after each round, the relation defined by the current positions of the pebbles is a partial isomorphism. So rather than just sort of having a limited sort of incremental investigation into the structure, we have a sliding window delineated by the pebbles, and we can move the pebbles around so the window can move, but the size of the window is fixed, and it's this which bounds the resource, not the length of the play. Whereas the k-round Ehrenfeucht-Issei game corresponds to bounding the quantifier rank, k-Pebble Games corresponding bounding the number of variables which can be used in a formula. And of course, there's the same variations in existential positive version in which spoiler only plays in A and duplicator responds in B. Now, the point is that we can run exactly the same script as for the Ehrenfeucht-Issei case. I'm not going to describe that in detail, there isn't time, but I just want to make the point here. There's a category of k-pebbled forest structure, so we add a pebbling information and an extra condition relating to that. And in the same way as we saw in the Ehrenfeucht-Issei case, there's a resource indexed adjunction with relational structure. So we're studying the same extensional category, relational structures, from a different resource sensitive lens using this pebbling idea. We can define paths, pathwise, and we can run the same script then. Once we have these general definitions, remember, instantiating an axiomatic framework, we can define paths, pathwise embeddings, open maps by similarity in exactly the same fashion as we did for the previous case with the Ehrenfeucht-Issei. Hence, we can define bisimulations between objects of the extensional category using the resource category. So we get these 3 relations defined in exactly the same way, homomorphisms both ways, bisimulation, existence of a span of open pathwise embeddings, in other words, and isomorphism. And now we take, if we take our resource indexed fragments of first order logic to be now the K variable fragments rather than the quantifier rank fragments, then we can get verbatim the same result with respect to these logical equivalences. So everything goes through, I mean, some of the arguments are slightly different. Well, I mean, most of it is the same, but we have some differences. And interestingly, we can also look at the coalgebras. We have a comonadic adjunction. We can define the coalgebra number in exactly the same way as we did before for the Ehrenfeuer-Isse comonad. And now we can show the nice fact that for this pebbling comonad, the coalgebra number of A corresponds precisely to the tree width of A. So again, we get that. And this is just the beginning. So we now have quite a number of examples where this works to give us, I mean, really to explore a large landscape of fragments of first order logic, looking now also into monadic second order logic. But we have basic modal logic fits nicely into this. In that case, the comonad is essentially performing the unraveling construction. Recently, we've looked at hybrid logic and other significant extensions of basic modal logic. The guarded quantifier fragments have been important in pushing the envelope of tractability far beyond modal logic. These are very nicely covered in various versions of what are allowed as guards. Also generalized quantifiers, path width, and other things. In each case, we have tight connections with logical fragments and with combinatorial invariants. And the connections, so the coalgebras or Eilenberg-Moore categories play an important role. And we get direct descriptions of the coalgebras in terms of comonadic forgetful functors. And these are important both for formulating bisimulation, as we've seen briefly, and also for the connection with combinatorial invariants. So there's a bunch of papers which lay this out. As I mentioned, there's an axiomatic development in this paper with Luca in this year's iCal. And we, of course, want to use this to get both conceptual formulations, but even better extensions and generalizations of various results in the area. So we have various new results of the semantic or model theoretic characterization preservation theorems of the kind perhaps best known from Van Bentum's theorem characterizing modal logic in terms of bisimulation invariance. So we have also results that work uniformly in the finite and general, including infinite cases. So they're not dependent on model theoretic methods that don't work in the finite case. And recently there are Lovash type theorems on counting homomorphisms and so forth. Okay, well, and here's a few, some of the papers that I was mentioning. So thanks very much for your attention.
Thank you very much, Samson. Questions, remarks? Ron, you have a question?
Yes. First, since you're talking about, this is a conference for Trachtenbrot, so I want to make one recollection connected with Samson. When we're discussing and studying much earlier works of Samson, Trachtenbrot used to call him Shimshon HaGibor, Samson the hero.
I see, I didn't know that.
And I assure you, no offense, it didn't mean your physical strength. That's I can assure you.
I could have guessed that, yes.
So,
yes, if I can add one thing I do remember is that I remember giving, this was in the early days of linear logic, and I remember giving a talk which I called something like Linear Logic, a Guide for the Perplexed, which, you know, is a translation of Morena Buchim. And so the Boas, in a very nice way, said that it was still possible to be perplexed even after the talk, which was certainly true.
Okay, so my question will be also in the spirit of Boas, of Trachtenbrot, that was didn't mind to ask difficult question. So, how difficult it will be for you to restate your results and ideas without using the categorical language?
I think it would be difficult.
Because some people, few people, but there are some people that somehow have problems with category theory.
Yes, I know. There are people who are co-category theorists. Yes. Yeah, it's a very fair point, and I agree that it can often be good to strip out unnecessary things. I do. The thing is that here the concepts really fall very naturally, really apply very naturally to the things that we're studying, and I think it would genuinely be difficult to completely abstract that away. In particular, I mean, there are sort of clusters of concepts. I mean, adjunctions, Galois connections, not so unfamiliar really, but and then comonads, I mean, closure operators and so on. But you get a lot extra by taking the morphisms into account. And in particular, for example, these coalgebras correspond exactly and bijectively to decompositions of the kind that you get in the tree decompositions as you have in tree width and these other kinds of combinatorial invariants. So a coalgebra of the kind I was mentioning here, for example, I guess here. So a particular coalgebra is a witness that the tree width of the structure is no more than k if it goes to the resource index k. So I think it's I would say the use of category theory is genuinely useful here, but maybe one could disentangle it. But I mean, on the other hand, it's also good to try and push beyond and actually make useful contributions to results. So, for example, the beautiful work by Dawa, Yakel, and Reggio on these Lovash type theorems recently. That was in LIX of this year, and then a follow-up paper. And they got new results that fall out from this general way of looking at. So Lovash theorems are characterizing isomorphism it was originally graphs, but then it extends to relational structures. So they characterize isomorphism in terms of the number of morphisms into the structure, typically. The famous result from the 1960s. And then this has been extended in various ways. I mean, these results by Martin Groh and so on. And you get a general perspective on this. So you get some new results in that paper. And now in a recent work of Luca Reggio, has a further extension that also applies to various infinite structures. So I mean, I entirely I agree that I understand the spirit of your question, but I don't think it would be a trivial matter to strip out the category theory. And on the other hand, I think the promise is to use this machinery to get interesting, concrete results. And as I said in that, however distant a prospect that is, I mean, as I said in my opening slide, they wrote a big program, had a lot of abstract stuff, but eventually it sort of has some payoff in concrete questions. So that's my feeling, that this is. I mean, we should also remember, by the way, that there are people over in, track A who are skeptical about logic in much the same way. You really need logic to get your results, they might say. And I don't think you're going to agree that you could get rid of the logic. Anyway, so I think that's what I can say by way of an answer. Thank you for the question.
And thank you very much.